this will be qualitative insights on the wave function. It's qualitative, and it's partially quantitative, of course, insights into energy, into, let's say, real energy eigenstates. So whenever you have a problem and a potential, we have what is called the total energy, the kinetic energy, and the potential energy. So you have the energy, which is total, equal a kinetic energy plus a potential energy. Now the potential energy, as you've seen, sometimes depends on position. We did piecewise continuous and potentials, but they could be more complicated, do funny things. So this is a function of x. And classically speaking, we speak of the energy. You see, in quantum mechanics, the energy is an observable, is the result of a measurement with a Hermitian operator. Sometimes there could be uncertainty, sometimes not. But in classical physics, which this intuition will come from, well, you have a total energy. This conserved is equal to potential energy, a kinetic energy that will also depend on where the particle is in a potential. Let's do a very simple case. Coordinate x, a potential v of x. Is this the potential v of x? It's a constant, nothing that complicated. And suppose you have a total energy. Now the total energy in classical mechanics is conserved. So when I draw a line, I'm not implying that it's a function of x, that sometimes the energy is like that. No, it's just a number there that I fixed. Here is the energy. And then wherever you move, if the particle, the classical particle is here, then it has some potential energy v of x and some kinetic energy k of x, building up the total energy. Classically, the kinetic energy determines a momentum. The kinetic energy is p squared over 2m. Now the kinetic energy is p squared over 2m. In this case, the kinetic energy is a constant. The momentum will be a constant. And then what we really want to just say something about is the wave function. Well, but if we know the momentum classically is a momentum p, we can infer the de Broglie wavelength of the particle. And the de Broglie wavelength would be h over p. And that's for the wave function. So we should expect a wave function that has a wavelength equal to lambda. After all, that is what de Broglie did. And from de Broglie, you got the Schrödinger equation. The Schrödinger equation, in fact, says this, if you look at it again. So if you look at the wave function, well, it must have wavelength lambda, and therefore I'm talking about real wave function. So it could be a cosine or a sine that has that wavelength lambda. Of course, in quantum mechanics, a cosine or a sine doesn't have exactly, it's not an eigenstate of momentum, but it's an eigenstate of energy. And we want to plot eigenstates of energy, so you will have something like that with that lambda. And that's sort of the intuition. You go from the diagram to a kinetic energy, from a kinetic energy to a momentum, from a momentum to a wavelength, and that's the wavelength of your energy eigenstate. And maybe it's a good idea that you try to convince yourself this is true by looking again at the Schrödinger equation for this simple case of a constant potential and an energy that is bigger. You will find this result very quickly. But let's do now a more interesting case in which here is x, and the potential is a growing function of x, and there's a total energy here still. So if you are at some point here, here is the potential of x, and now this is k of x. And now comes the interesting thing. You see, as the particle, whatever particle is moving here, the kinetic energy is decreasing as you move to the right. So the kinetic energy comes with some velocity and slows down, slows down, slows down. The kinetic energy is becoming smaller and smaller. Therefore, the momentum is becoming smaller and smaller. And therefore, the wavelength, the de Broglie wavelength, must be becoming bigger and bigger. Now, that is not exact, because you really have to solve the Schrödinger equation to do this. But intuitively, you know that if the potential is constant, this is absolutely true. The kinetic energy and the momentum and the de Broglie wavelength are related in this way. It will be sort of true or approximately true if the potential is not changing that fast, because then it's approximately constant. So there's a notion of a slowly changing potential in which we can talk about the k of x that is decreasing as we move to the right, a p of x that is also decreasing, and a lambda of x that would be increasing. A wave with a de Broglie wavelength that is increasing. Now I should have written them here, maybe k of x, p of x, lambda of x. This is decreasing, decreasing, increasing. So I can plot it here. And I would say, well, I don't know exactly how this goes, but maybe it's the wavelength is small, and then the wavelength is becoming bigger, something like that. Well, the wavelength becoming bigger in the energy eigenstate that you will find is true. But there's also the question whether the amplitude of the wave will change or not. So we'll answer that in a couple of minutes. But the de Broglie wavelength now is kind of becoming a function of position. Now, you know that solving the Schrödinger equation now with an arbitrary potential is a difficult thing. With a linear potential, it's a difficult problem in which the exact solution exists in terms of airy functions and things like that. So this can only be an approximate statement that the de Broglie wavelength is becoming bigger and bigger because the momentum is becoming smaller and smaller. But it's a very useful statement, and whenever you look at wave functions of potentials, you see that thing happen. Questions? Let me draw another diagram that illustrates these issues. So, three erasers and all crammed together. So let's draw a general picture of a potential now, so we can make a few features clear. So here it is. We'll have a potential that is like this, V of x, maybe some energy E, And that's it. Now, what happens classically? Well, if the particle has some energy, you know already this part is V of x, this is K of x. There is a potential energy and kinetic energy. The kinetic energy cannot become negative classically, so the particle cannot go to the left of this point called XL, x to the left. So this region, x less than x left, is the classically forbidden. Similarly, on the right, you cannot go beyond here because then you would have negative kinetic energy. So this is an x right, and everything to the right of x right, x greater than x right, is also classically forbidden. These points x left and x right are called turning points. Because those are the points where a particle, a classical particle that it lives in this potential, has to bounce back and turn. As we mentioned, at any general point, you have V of x and K of x. And this point, for example, is the point with maximum K of x or maximum velocity. This is the point where the particle is moving the fastest. And it always kind of slows down as it reaches the turning point because the kinetic energy is becoming smaller and smaller. So, as we said, if you had a constant potential, this would be the solutions. Constant p, constant lambda, nice simple wave function. If it's not constant, well, nothing is guaranteed. But if it's sufficiently constant or slowly varying, then you're in good shape. Now, what is the meaning of slowly varying? The meaning of slowly varying is, has to be said in a precise way. And this is what leads eventually to the so-called WKB approximation of quantum mechanics, that we're sort of giving you the first results of this approximation, that you can understand classically how they go. To mean that you have a slowly varying potential is a potential whose percentage change is small in the relevant distances. Wow. So it's the change in the potential over the relevant distance must be small compared to the potential. But what is the relevant distance? If we use the intuition from quantum mechanics, is the de Broglie wavelength at any point. That is sort of what the quantum particle sees. So what we need is that the change in the potential over a de Broglie wavelength, take the derivative multiplied by the de Broglie wavelength, must be much smaller than the potential itself. And notice, of course, the potential is a function of x, and even lambda is a function of x. There's the kind of the de Broglie wavelength. Now, an exact solution will not be a sine or a cosine, so to say it has a precise defined wavelength is an approximation. It's the approximation of slowly varying, but it's a nice approximation. And this lambda is the lambda that would come as h over p of x, and h over p of x is the square root of 2m times the kinetic energy over h squared. No, no, it's just that, square root of 2mk, of course. square root of 2m k of x. I'll write it nicer, k of x. Okay, so the idea is that you can roughly say, okay, the de Broglie wavelength here is of some value. Here the momentum is small, the de Broglie wavelength is large, and so when you draw things, you adjust that. You say, okay, here the momentum is large, therefore the de Broglie wavelength is small, so you write a short wavelength thing, and then it becomes longer wavelength, and then shorter, and you just try to get some insight into how this thing looks.